Okay, let's go ahead and get started. I'm Charlie Smith, Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and scale. This will be done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. More information on the G-PST can be found at globalpst.org. ESIG serves as a lead of Pillar 1, and as such would like to welcome you to our monthly joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and will focus on the research agenda and research questions being addressed in Pillar 1. Topics will be presented by both the founding system operators and other advanced system operators active in Pillar 1, and members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we are going to be using the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG9 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar consists of a presentation on grid-forming inverter applications. Based on the number of registrations, this is shaping up to be another all-time favorite. The interest around the world in inverter-based resources is intense, particularly in grid-forming inverters. Today's webinar will feature 2 members of the G-PST core team who are very active in the grid-forming inverter agenda of both ESIG and the G-PST. Julia Matevosyan is a member of the staff at ERCOT, and Jason MacDowell is with GE Energy Consulting. Julia serves as the chair of our ESIG High Share of Inverter-Based Generation Task Force and is a member of the Inverter-Based Research Agenda team for G-PST. In her position as lead planning engineer at ERCOT, she studies a range of related phenomena, including adequacy of system inertial response, and frequency control and performance issues related to high penetration levels of inverter-based generation. Jason is the chair of the ESIG Reliability Working Group, of which Julia's task force is a part, and is also a member of the Inverter-Based Research Agenda team for G-PST. He has 20 years of energy industry experience in a broad range of power system engineering, planning, and operation issues. Julia and Jason are both good friends, and I feel very fortunate to have them both here with us today. Today's webinar will focus on grid-forming technology viewed as one of the necessary enablers for high penetration of inverter-based resources. While still an area of active research, grid-forming battery energy storage systems are already commercially available and are being used in a number of applications around the world. This webinar will provide a review of some of these projects, focusing on the drivers behind the choice of technology and project performance. Okay, just a short reminder once again to use Slido at slido.com, with the event code of ESIG 9 to ask your questions. And without any further ado, let's go ahead and get started. Julia, I will now turn it over to you.
All right, Charlie. Thank you so much for introductions. Can you hear me?
Yes, we hear you loud and clear.
All right. So without any further ado, let's just move on with the presentation. Yes. So as Charlie mentioned, I'm chairing High Inverter-Based Resource Task Force under Reliability Working Group at ESIG. And so one of the recent efforts that we're working on right now is developing a white paper. Yeah, I just skipped to mention that the objective of the group is to develop understanding of the options for stable operation of future power systems with very high share of inverter-based resources and roadmap for making the transition from power system the way it is today to where it's headed with high share of inverter-based resources. We have research organizations, O&Ms, and system operators participating in the group. And so, yeah, as I mentioned, one of the work products of the group is the white paper on the role of grid forming technology to enable energy system integration. And here you can see outline for the paper. We'll talk about system needs. We'll talk about technologies to serve these needs, including existing technologies and developing technologies. We'll provide brief description of grid forming control methods, a characterization of grid forming resources to support system needs, so kind of from the perspective of what grid forming inverters are able to deliver. Then there will be international project references of grid forming applications, experiences with interconnection requirements for grid forming resources, discussion on study tools that are needed, and then we'll conclude with future outlook for grid forming resources. So as I mentioned, we only recently started working on this paper. Some work is going on, and in today's webinar, I'm going to concentrate on international project references for grid forming applications and also touch on experiences with interconnection requirements for grid forming resources. So there's two topics highlighted in red. That's what I'll be talking about today. So I want to give a disclaimer that none of this work that I'll be presenting today is my own. There were people who directly sent me contributions for the white paper, for this particular section of the white paper. And then I also use a number of references, and I have people listed here who authored those references. And there were many other people that contributed as well. So I just wanted to thank them all. So just to set the stage, and make a difference, what we mean by grid following and grid forming definitions. I pulled up definition from the white paper. So grid following are inverters that we mainly have on the grid today. They are relying on fast synchronization of external with external grid to tightly control the active and reactive current outputs. If these inverters are unable to remain synchronized with the grid or under challenging system conditions, they are unable to sustain controlled and stable output. For grid forming inverters, primary objective is to maintain internal voltage phasor, and when grid forming controls are applied in bulk power system connected IBRs, the voltage phasors is held constant in subtransient and transient time frame. This allows IBR to immediately respond to changes in external system conditions and provide stability in controls during challenging network conditions. This phasor must be controlled to maintain synchronous with other devices on the grid and control active and reactive currents to support the grid. When grid forming controls are applied in non-BPS connected IBR, so for example, for black start or microgrids, the synchronization functionality is removed or limited, and voltage phasor may be held relatively constant over time. This allows plant to operate an electrical island and defined grid frequency for the entire island. There are many variations of grid forming and grid following converter controls, and both are subject to physical equipment constraints, including voltage, current, and energy limits, mechanical equipment constraints in wind turbines, as well as external power system limits. So with that, I'll move on. You've probably seen this slide before from me. This is my favorite circular problem. As we integrate more and more inverter-based resources on the system, it becomes challenging for system operators to keep system reliable and stable. And it's also challenging to require additional functionality from inverter-based resources, which are not currently commercially or widely available. So what it results in that operators are forced to apply transmission constraints or other operational constraints. This leads to curtailments. It becomes more difficult to connect further inverter-based resources. Either it's not economic or it's not permitted by system operators in different systems. This may result in shrinking market volumes for OEMs, and then OEMs don't have clear specifications of what is needed from inverter-based technology for the system operators to provide. And there is no standardization so that OEMs can develop these capabilities. So one of the solutions to the circular problem that people are testing in different parts of the world are these pilots or test projects in the field. And also another angle that I think people are approaching this problem from right now is developing minimum specifications for inverter-based resources, for grid-forming inverter-based resources, to get to capabilities that are needed for the system with high share of IBRs. So I looked around at what projects are available around the world, and also, as I mentioned, task force members contributed with that. There is actually just a handful of pilot projects available, and I would encourage you, if you're listening now and aware of another project that is not mentioned here, to please reach out to me and provide more information, because we're still looking for use cases. So here's kind of outline of the rest of my presentation. I will talk about number of batteries for microgrids and black start application in that GE has deployed. I'll talk about battery in grid-forming battery in St. Eustatius Island deployed by SMA. I'll talk about Dersalloch wind farm in Scotland deployed by Siemens Gamesa, the Rimple battery in South Australia by Hitachi ABB, Thorndale Battery in South Australia by Tesla. And then I'll kind of switch gears to drivers behind those grid forming trials in Australia. You can see I have two projects from Australia I mentioned. And also Stability Pathfinder in Great Britain, and proposed non-mandatory grid forming interconnection requirements that are currently under consideration in Great Britain as well. All right, so there is a number of grid forming batteries that GE had deployed. Two of them on the list here are for microgrid application, the oldest being for Matlakatla community in Alaska. So this is just a pure microgrid application. In Vernon, California, this application is to increase reliability of supply for industrial load. So at times this battery is operating grid connected mode, and at times it's powering up that local load in islanded mode. The rest of the projects on the list are black start applications. So this is where grid forming battery is being used to power up auxiliaries on heavy duty gas turbines. So basically those gas turbines can be started without being connected to the grid or any other synchronous generation in vicinity. Once the auxiliaries are powered up, that basically turns that gas turbine into a black start unit, and it can provide black start capability for the rest of the grid. So what's done in this project, the battery is added to gas turbine. There is very little modification that's needed to original plant. And soft start is used in grid forming battery to gradually increase voltage, and this way limit inrush currents at the motor start and transformer energization. I also wanted to mention that GE and with many other participants is participating in DOE-funded SETOR project, Advanced Grid Forming Inverter Controls, Modeling and System Impact Study for Inverter-Dominated Grids. That project started in 2020 and has GE, First Solar, NREL, and a number of universities as partners in the project, developing controls for grid-forming inverter. Another example is microgrid in St. Eustatius. SMA actually deployed a number of microgrid types of projects on a number of islands, but this is one of the on which information is more widely available. The peak load of the island is 2.3 megawatt. Yearly energy consumption is 14 gigawatt hours. Initially, the island was powered by 9 diesel gensets, so which makes power supply very expensive. At some point, solar was 4 megawatts of solar was added, and a 1 megawatt battery, which was grid-following battery, and then as a second phase, additional over 2 megawatt of grid-forming battery was added. So the overall plant controller sends start and stop signals to genset. It does frequency and voltage control during genset free operation, so when genset is not online. And then once genset is online, it transfers frequency and voltage control to the genset controller. Load distribution is done on several parallel grid forming units. So there are 2 grid forming inverters. And there is no external communication required. They tested the project in diesel off mode in a testing stage, and now diesel is being off in the middle of the day when it's sunny and there is sufficient storage. There is seamless immediate load transfer after generation contingency, and contingency has happened where all entire genset was lost and frequency dipped 0.6 hertz. The frequency was restored within 3 seconds, and no load shedding was necessary. Also, voltage write-through for various faults was tested during operation. So this is kind of one of the examples of successful deployment of grid-forming battery in island application. This project is where grid-forming control was applied in 23 direct drive full converter wind turbines, 69 megawatt wind farm. The wind farm is existing wind farm. It was designed as grid-following wind farm initially, but it was controls were modified and it was tested in grid-forming modes for 6 weeks in 2019. There, its virtual synchronous machine control method is used. Virtual inertia constants that were tested during trial were from 0.2 seconds to 8 seconds. When I'm saying virtual inertia here, I would like to mention that it is using kinetic energy of rotating wind turbines. This is different from what's been termed as synthetic inertia, since this is not requiring any external frequency measurement. So when inverter is operating in grid forming mode, it behaves like a virtual synchronous machine, and it uses energy from rotating mass of wind turbines as energy storage or energy buffer. There were 6 large under-frequency events during the trial, just that naturally happened on the system, with largest rate of change of frequency 0.11 hertz per second, and the largest frequency drop down to 0.5 hertz, the delta F being 0.5 hertz. Additionally, a large frequency event has been induced and tested with inertia constant of 8 seconds, and all responses that they've got during the test were as expected for inertia constant set. There were no significant voltage steps during the trial, and so the largest voltage phase steps, and the largest that been encountered was 0.2 degrees. The wind power plant was able to respond autonomously and immediately with power injections as expected, with inertia levels as they were set. There were no turbine trips due to stalling over power over current during this trial. Limitations that's been reported, and that's understandable, is that wind turbines' ability to respond will be affected by wind speed declining during response. So, for example, if you have under frequency event and wind turbine is providing virtual inertia response, it may be affected if during the same time wind speed is decreasing. And then wind turbine's ability to respond at low or zero power output is extremely low, since rotational speed is lower. All right. So the next test that they've done on that same wind farm in fall 2020 was to demonstrate islanded operation and black start operation. So in this case, they were able to show that a wind farm can operate autonomously in islanded mode. They tested all the way from all wind turbines operating in grid forming mode down to a very small number of wind turbines, just trying to understand how small of a number is needed. And they were able to determine that just very few wind turbines need to be in grid forming mode for an island to operate successfully. Initially, the tests were done to just operate auxiliaries of the wind farm and not having any load supplied. And then also they tested load steps of 7 megawatt, where they connected 7 megawatt load bank. And again, in all the tests, successful operation as expected was demonstrated. And then they were also able to successfully resynchronize the island from islanded grid back to grid mode operation. For black start, it was a bit more difficult. Just to power auxiliaries, as in the example of GE, where a battery was added to help gas turbine to become black start unit. Here they added little small diesels to power out auxiliaries of wind turbine. That probably could have been done with the battery as well, but required more modifications to controls. And so diesel was used as a proof of concept. You can see that diesel is relatively small. It's 125 kVA, and just to put it into perspective, turbine is 3.4 MVA each. So diesel powers up auxiliaries of the wind turbine, and after that, wind turbine can operate in grid forming mode and black start the rest of the island, and then be resynchronized with the rest of the grid. So with just this 4 grid forming wind turbines with now black start capability, they were able to energize the entire park, 33 to 132 kV transformer, the overhead line, and all the way to 132 to 275 kV transformer. They also used soft start, so where voltage was gradually increased to reduce inrush currents, but they also found that because it's providing black start capability for the bigger island, and then eventually will power up the bigger portion of the grid, then elements of the grid are exposed to lower voltages for longer times. And so that maybe is not a very useful strategy. And they tried different strategy where a number of wind turbines were started simultaneously, bigger number of wind turbines started simultaneously, and transformer tap changers were also used to gradually power up the rest of the grid, and this way to provide inrush currents that were needed by transformers. So the next example is Hitachi ABB energy storage in South Australia. This is the largest grid-connected grid-forming battery in the world that at least we are aware of. It's 30 MVA, 8 megawatt hours. It's also operated in virtual synchronous machine control method. It's first large grid-forming battery connected to Australian transmission system. So they have other applications. One of them is also by Hitachi ABB, where same size battery is powering up a coal mine, but this is microgrid application, whereas this one is actually connected with Australian transmission system. It is installed in 2018 near the end of long 132 kV single circuit radial feeder, and it's close to 91 megawatt wind farm. It also has local load connected at the substation with a peak load of 8 megawatts. There is also 2 megawatt of local rooftop PV connecting into that substation. In the first 6 months of operation, it's shown that this project reduces loss of supply in the area from 8 hours to 30 minutes. So it helps when interconnection with the rest of the grid is lost, then this part of the grid is being operated as an island, and this way supply is retained to customers. So services provided by this project include inertia. It can provide virtual inertia response, reducing rate of change of frequency during sudden loss of generational load. This is different to fast frequency response. Again, it doesn't need frequency measurement to respond and kind of responds in the way a synchronous machine would do. There is instantaneous injection of active power in response to change in voltage angle. It can operate at very low short circuit ratios, and it's also able to provide support via short-term current overload to the system. As I mentioned, it can do islanded operation, regulates frequency of the microgrid using virtual inertia. It also provides primary and frequency control, primary and secondary frequency control. It can adjust system frequency when there is over generation on that island system by increasing system frequency, and that causes distributed PV to trip offline. So this way it can regulate against over generation on an island when operating in island mode. It has black start capability, so it can black start a local 33 kV distribution network with 8 megawatt demand, and then again voltage is ramped up slowly to limit in rush currents and harmonics. Another functionality that it has, it's not related to grid forming capability. It could have been done with grid following battery. It provides fast active power injection into grid following significant loss of generation. Here battery, it can inject full capacity within 250 milliseconds if network event is detected and AC interconnector from South Australia to the rest of the grid is tripped. So it's basically like a special protection scheme where battery would provide fast frequency response. So as I mentioned, for this, it wouldn't have to be a grid forming, but just to mention that this battery provides this service. And another interesting one, and it's relatively recent information. You probably all heard about Thorndale Battery. It used to be the largest battery in the world, 100 megawatt, 129 megawatt hours. It provided energy and frequency control ancillary services in Australia. It was installed in 2017. In 2020, in fall, it was expanded to 150 megawatt and higher energy capability. Currently 2 inverters there are operated in virtual machine mode and so being tested. Virtual machine mode component runs in parallel with conventional grid following component, so it can switch mode between grid forming and grid following effectively. And so under stable system conditions, the inverter will behave like a grid following inverter, and during grid disturbance, it will produce active power response proportional to rate of change of frequency and inject reactive current in response to changes in voltage. This one was recently real-life tested in frequency event created by a coal plant explosion and then subsequent trip of neighboring units. So there was a frequency event at the end of May. And so what you can see on the right-hand side in purple, it's frequency trace. And in red, response. So on the upper plot, what you can see is the response of the entire plant, and it still looks like kind of fast frequency response proportional to frequency deviation. You can see that response starts after frequency starts dropping, and peak of response is reached at the same time as frequency nadir. Whereas on the lower plot, you can see a response from those two inverters that were operating in virtual machine mode, and you can see that response is kind of ahead of frequency, and peak of response is reached even before the nadir, and so that's kind of a response of virtual inertia from this from two inverters operating in virtual machine mode. So as I mentioned two battery projects in Australia. There is a couple of more in the pipeline right now, all BPS connected. And so I wanted to talk a little bit about drivers for this in Australia. Australian Energy Market Operator enforces minimum inertia and system strength requirement in parts of the grid, one example being South Australia. So new inverter-based resources also should not reduce system strength in the area. And then screening and full interconnection studies with EMT are being done to assess impact and propose mitigation measures such as network upgrades, synchronous condensers, contracting with existing synchronous generators, use of grid forming technology, controller tuning of existing inverter-based resources, and remedial action schemes. And then interconnecting entity is responsible for cost of implementing these measures. So this is one of the drivers where people are trying to test grid forming technology and provision of inertia and supporting system strengths in the area where there are requirements. Another motivator for deployment of grid forming technology is a national grid in Great Britain. There were two Stability Pathfinder projects, two phases of Stability Pathfinder project, where they were trying to look for solutions to provide inertia and system strength in parts of GB. And with this, they were looking for commercial solutions alongside as network owner solutions, and then trying to do cost-benefit analysis and decide which solutions are more cost-effective. And so on the right-hand side, you can see requirements for the first phase of Stability Pathfinder. So the main features that they were looking for is short circuit level contribution, inertia contribution, and then steady state voltage and frequency support, transient voltage and angle stabilization, fast fault current injection, higher or relatively high rock-off withstand, transient over voltage, and then they were also asking for performance under a certain level of existing system strengths so that the plant doesn't trip. In the second phase, again, they were looking for system strengths in parts of Scotland on the grid. And here, in the first Pathfinder, it was restricted to traditional technologies, so synchronous generators and synchronous condensers could participate, and it was awarded to 5 synchronous condensers in 7 locations. Whereas in the second stage of Stability Pathfinder that's going on right now, even inverter-based technologies are allowed to participate. For inverter-based resource, for inverter-based technologies, voltage source behind impedance behavior is required. Inertial power needs to be provided within 5 milliseconds. Phase jump power, fast fault current injection, and power oscillation damping. There are more requirements. These are just additional to what was in the first stage of Pathfinder. And then also to both Pathfinder stages, existing grid code requirements apply as well. So the solution should comply with existing grid code requirements. So during this time, when the first phase of Stability Pathfinder was already going on, there was a expert group formed that worked on minimum specifications for, initially it was called virtual synchronous machines, but then they expanded it, and now it's called for grid forming inverters. This group provided developed minimum technical specifications for grid forming inverters. These requirements were then converted to Gridcode proposal, and these requirements are proposed as non-mandatory requirements. And the idea is that after requirements are approved in parallel, there will be development of market for system services. Essentially, again, provision of system strengths and inertia, and these will be commercial markets that will incentivize these capabilities. So the idea of a grid code requirement is just to say, if you're providing this service, these are capabilities that you need to have. And again, the resource that providing this grid forming capability should act as internal voltage source behind reactance, should maintain synchronism stability up to 60 degrees phase jump, supply rate of change of frequency power. So what this means, initially it was separate inertial power and frequency response, but then to make it broader and allow application of grid forming inverters that don't have virtual inertia, this was converted into this rate of change of frequency response power. So that would include inertial response and frequency response capability. And so a resource would have to describe what capability they have, and they would be valued accordingly depending on how this market is designed. Then there is a requirement to withstand 2 Hz per second rate of change of frequency, requirement to phase jump power that needs to be provided, damping, fast fault current injection, and control-based real and reactive power injection. Control power should be provided with bandwidth less than 5 Hz to avoid oscillations. There will be minimum short circuit level at which device is expected to operate, and that will be bilateral because it will depend on location for the service. It must inject current for balanced and unbalanced faults, and current should increase with fall in retain voltage without exceeding peak current rating. So this is also important. There is no requirement to oversize inverters. It just the provider of the service would need to inform what is the peak current rating, and then it should comply with requirements, other requirements within its rating, and not go beyond it. So there is no requirement to oversize. And then there are extensive descriptions about how tests and simulations will be done to verify these capabilities. And so on the right-hand side, you can just see comparison between conventional grid following inverters, grid forming inverters, and grid forming synchronous generators providing these functions. And so you will see, if you look across capabilities that are required, you will see that basically in this specification, the target was to achieve same or similar performance attributes that synchronous machines are providing today. So just kind of go back to the circular problem and where this all leaves us, and dissect it a little bit and conclude this presentation. So there are changing system needs with changing generation mix. In parallel, technology is developing to address some of the system needs, but there is a disconnect. So there is this middleman in green that you can see on this picture that is between grid operator and OEMs, and this is a developer. And so the developer will only go for functionalities that are either required or paid for. And so unless there is incentive to provide any additional capabilities, the developer will not ask from OEMs for these capabilities. And so there is lack of unified kind of policies and practices that will tell developer to go for capabilities that system needs. And so what's important for system operators is that now we have all these inverters on our system, and we would like to operate them all in reliable and stable manner without interactions and under all system conditions. We need solutions for loss of synchronous inertia and support of grid frequency to keep systems stable. We need solutions for system restoration, black start, and weak grid conditions and stability. There is lack of tools, modeling, and planning practices that fully identify risks and capabilities of equipment to mitigate risks. But overall, I think there is lack of grid codes and interconnection requirements and market mechanisms that would play this critical role in deploying these new technologies and capabilities, like grid forming inverter-based resources to meet the grid needs. There is a need for collaboration between regulators and system operators and equipment owners and OEMs to define requirements and mechanisms to deploy this new technology and break this circular problem that I started with. One more thing I just wanted to mention, going through all these trial projects and pilots, it becomes very clear that the applications that are being developed right now, they are very custom based. So they're based on existing problem, existing system conditions, and designed for particular application. So for example, in Australia, because there is a driver to provide this particular inertial response or system strength, this is what it's designed around, and it may not fit, this application may not fit for other grids. So thinking about OEMs, probably harmonization and more kind of plug and play solutions would be more cost effective to develop. And this is something where more work is required. Another thing I just wanted to mention is that looking for these real world projects, it's really hard to understand all details of control strategies that are being used and why they're being used. So it seems like a lot of these solutions are very proprietary, and understandably so, but also it kind of limits our understanding as a system operator of how it would apply on our system. And so with that, I wanted to thank you all for your attention, and we'll be ready for questions.
Okay, thank you, Julia. A lot of good information there and a lot of good questions popping up here. So before I go into the Slido questions, let me just kind of ask a follow-up question on that last slide, going back to the first slide and the last slide with the virtuous or the maybe not so virtuous circle. What's your feeling? How do you and Jason read the situation with regards to the progress that's being made in solving the circular dilemma? Are we making progress? Have you seen progress in the last year or two? Do you think there's anything on the horizon that's going to make a big change, or is it just kind of a slow, steady slog?
I think, from my perspective, that Jason may add and have a different perspective. So I am looking at all projects preparing for this webinar. I think there is progress being made, and I think understandably so, you see this projects being deployed in areas where it's somehow incentivized. There is some kind of indication that the services will be needed. There is some kind of definition what this service means, and this is where these pilot projects are being developed. So it is a bit chicken egg. It's you need some kind of requirement or incentive and clear description of what this product is supposed to provide before the pilot is deployed. But then on the other hand, this pilot being deployed kind of show us what capabilities are there, and maybe we other system operators may learn from that experience. Jason, want to add anything to that?
No, I think you hit it well, Julia. And I think what's different now, and you pointed this out well, is that it takes an understanding of the need of, what is different? What does the system need that the existing controls or topology can't meet? And then what else does grid forming, for example, allow or do? And the pilot projects that you pointed out, Julia, I think show that there's certainly capability of the technology, albeit it's early adoption, but it's capability of the technology to meet some of those capabilities. But then there's a whole bunch of other aspects to the deployability that you pointed out. It's making sure that the models that are being used to determine overall how these resources can support the grid in higher penetrations for control stability, for supporting frequency and voltage when it's needed. So I think all of those new capabilities coming out in the pilots are going to be reflected ultimately back in the models that are used in the system studies to determine what system conditions need to resolve. And then you'll start to see a little bit more deployability and adoption. And then there's the other side of this where grid code standards and markets eventually evolve to say, okay, we trust this enough in order to be able to put it in place, and we have enough capability in equipment to actually get projects on the ground, meet requirements as needed, and then it'll start to take off. We've seen that in every aspect of the early adoption of ride-through, the early adoption of fast frequency response and control. We're seeing that in other aspects of performance as well, not only grid forming. But I think, Charlie, to your question, we're at the very precipice of this, and it is going to be a matter of how the controls are designed and how it ports over to system needs. But I think we've made a tremendous amount of progress to get to this point, but a lot more is needed to make it deployable.
Okay, thanks for that perspective. That's very interesting. And kind of a follow-up question, I guess, from Ryan Quint. It seems the common approach is virtual synchronous machines, inverters made swingy with mechanical dynamics of synchronous generators. Why? Is this preferred because it's familiar? When we can do so much better, why are we kind of sticking with what we know? Because that's what we know?
I think it's maybe because of the ask. So like in GB, I think the requirement came from that angle. So that being virtual synchronous machine it's because these are functionalities that are being provided by synchronous machines today, and they are going away. And so that's what we needed. It was easier to define services that needed based on synchronous machine properties. And so from that perspective, that's how the pilot project went.
It's kind of a straight replacement. Mm-hmm. Jason, what do you think about that?
Yeah, I agree. I think in the early adoption, Ryan, that's a great question, because there's a lot of talk about what's going to happen with frequency as we get higher and higher penetrations. And the natural concept or notion is, hey, you need a bunch of inertia to support the frequency from declining, and then you need enough, arresting energy and enough recovery capability to bring it back. And that's familiar. And those are definable things that are known well enough now that can be placed into grid codes to make it happen. To me, that's the easy step to require, but then there are other capabilities that we as an industry are still figuring out. The OEMs certainly have capabilities and bandwidth within our purview to make changes in designs in order to accommodate. But then how does that port over to supporting frequency maybe in new ways? We talk about fast frequency response to provide arresting energy. That's important. That can provide a lot of support. Granted, it's not exactly the same as inertia, but it also can provide support. But it's not as familiar as an inertia type function. So I would say, the adoption will take place over a period of time. Once you get used to some of the grid forming capabilities, there may be new tweaks to controls, new ways that those resources can support in slightly different ways with different performance that eventually will evolve. I think this is a journey, and this is one step along the way around virtual synchronous machines. So that's a good question, Ryan.
Yeah, it'll keep coming up, I'm sure. Okay, next question here is how much headroom should wind turbines have when working as grid forming sources? Any insights or guidelines on that?
So there was no intentional headroom kept on these resources. I think they've done some tests where it was kept, but to provide primary frequency response on top of inertial response. But for that virtual inertial response, no headroom is needed. It's just using kinetic energy of rotating mass. It causes wind turbine to slow down, and then caution must be taken not to go into stall and trip turbines. But other than that, no headroom was needed.
Okay. A question from Deepak here. What are the justifications used to determine inertial power injection within 5 milliseconds? Will the power system collapse if the power is injected in 20 milliseconds instead of 5? So you could kind of generalize that, I guess.
Yeah, so again, I didn't participate in those discussions. My understanding is that as to Ryan's question, that they were just trying to replicate inertial response of a synchronous machine, because that's what is there today and is familiar and studied and understood, and it's possible from grid forming inverter. I don't know,
Okay,
Jason, do you want to add anything to that?
No, I agree. And I think, Deepak, you're pulling on something that's really important around what is needed. When writing requirements or codes, it's very difficult, obviously, to try and understand how much do you need, when do you need it, why do you need it under all system operating conditions. Does 20 milliseconds work? Probably in a lot of cases. It works just fine. In other cases, you might need faster response, but not making it required so that you must do it all the time, and giving flexibility is a best practice to understanding what the capability needs to be and deploying that capability under different conditions. The other thing I'd like to mention, kind of with that question and the previous question about headroom, it's not so much about the operational constraint with grid forming. Grid following controls also need headroom to move around for primary frequency, but it's more about the energy management of the drivetrain and the buffer that's needed in order to deliver the appropriate behavior without causing undue stress on the drivetrain, without causing undue stress on the electrical system, to make everything balanced. You're looking at phase jumps, you're looking at other aspects to support the grid that ultimately has implications with grid forming controls regarding the amount of the transient energy that you provide with that. So that puts on a wind turbine, that puts a little bit more drivetrain stress, and it's a matter of design to manage that. But that's the bigger issue, not headroom.
Mm-hmm. Yeah, and then I see a comment from Andrew Isaacs in the chat, and rightfully so. It's like that 5 milliseconds is just to say instantaneous response, because from a grid forming inverter, you would expect it to be instantaneously. And so within this 5 milliseconds, that's the time frame that they put to maintain voltage, internal voltage source within sub-transient time frame, as per definition in the beginning of the presentation.
Okay. I'm going to skip over one here to the next one on what would be the implications of retrofitting existing grid following inverters, wind, solar versus battery energy storage systems, to grid forming from the manufacturer perspective. So maybe this is more to you, Jason.
Yeah, I'll leave it to Jason. It's just one thing I wanted to add from what I heard is that that would be more straightforward for batteries, maybe for solar resources as well, than for wind turbines, and Jason will speak to that. But for solar, you would need some kind of energy storage behind inverter to provide extra energy buffer. And then from storage, you would already have that energy buffer, so it's more straightforward and just about changing controls. Jason?
I don't know if I have anything to add. That was perfect from a manufacturer perspective. You got it, Julia.
Maybe more about mechanical drivetrain restrictions.
Yeah, absolutely. So I think the question about retrofitting and changing over, right, is one more about the design and what existing equipment that you have and what you're trying to do to change the control. It's not a huge issue to port over a new algorithm in an inverter or converter. That's the easy part. The more the part that needs to be looked at is what is the overall capability, the transient capability of that resource to be able to provide it? What's the energy source behind it? Do you need an energy buffer above and beyond where you currently have it? You said that, Julia. And then the stress on the drivetrain is the big one for wind. Was that accounted for, and can it maintain its life cycle if you convert from grid following to grid forming and any additional stress that's put on? Again, that's something that to me is manageable if you have another energy buffer that you could put in place. But this is all theoretical at this point. It's not that it's impossible, but you have to manage all of the application of the entire unit, the entire system, in order to make that work, not just the control itself.
Okay, how about this follow-up question related to the one that we just covered? Please comment on the overcurrent overload capability of the grid forming IBRs in some of the projects. How do the grid forming IBRs behave when they hit their current limits?
So that's a very good question, and that goes back to discussion that it's not very clear from references what is meant by overcurrent capability. Only in one project, as I understand, overcurrent capability was mentioned up to 2, and it also said 2 to 3 per unit overcurrent. So it's not clear what it means for existing project already. So and it's a short-term overcurrent capability. Again, not clear what short-term refers to. For national grid requirement, there is no requirement for overcurrent capability. So say for phase jump response, the requirement is up to 5 degrees phase jump. It should respond without hitting overcurrent capability limit. So that kind of gives an idea of sizing energy buffer. And then once it hits overcurrent limit, then it can limit current and keep it at that level, at 1 per unit to, it says 1 per unit to 1.5 per unit, but it will be up to developer to decide what to go for.
Okay. Anything to add, Jason? Is that good?
Yeah, no, I think, Julie, you hit it. The limits are the limits. It's a design consideration, and it is about the transient overcurrent capability as well. So it's Julie,
okay.
You said so. Thanks.
Quick question from Deepak. Are existing synchronous machines able to handle a 60-degree phase jump?
Yeah, I'm not sure about that. I mean, the requirements were designed with synchronous generators in mind as well. So I guess National Grid group that worked on that thought about that one. I don't know, Jason, if you want to add anything to that.
Yeah, I know that National Grid initially looked at a larger phase jump. They were at 90 degrees and relented back to 60. My guess is that looking at the overall capability of all resources to meet that phase jump criteria had a big hand in reducing that phase jump angle. So overall, the synchronizing torque in a synchronous machine obviously plays a role to help close the angle, but still, right, you have other considerations with transient stability in order to maintain synchronism that are limits for synchronous machines. That's a consideration, but you look overall at the capability of all resources on the grid, and to me, 60 degrees should be achievable. Again, it's a matter of design and how you harden the networks to be able to make sure under all system conditions that is achievable. That's the issue.
Sounds good. Question here. Why is Julia such an excellent and clear presenter? Oh, that's not a question. That's a comment. I'm sorry.
Thank you.
Question.
I'm sure you made it up, Charlie. No.
Do you expect that ERCOT will follow soon the example of National Grid procuring inertia and extra fault current with the Stability Pathfinder tenders? That's a big one for you, Julia.
I knew that would come. So I want to make a disclaimer that in this webinar, I'm speaking as a chair of high penetration task force and not from ERCOT's perspective. I mean, being system operator, we are looking at other system operators that are dealing with high inverter-based resources and kind of looking forward to learn from their experience. We haven't started anything material as pertains to grid forming inverters.
Okay, I'm sure that's a topic for some future webinars. All right, we're about at the top of the hour, 5 o'clock here, so I think we're going to need to wrap it up. Julia, Jason, thank you very much for a very informative and educational webinar. I know I learned some new things today, and I think everyone will find something to take away from it as well. As I mentioned earlier, an email will go out once the video file has been posted, and we'll get the answers to your unanswered questions posted as quickly as possible. We appreciate your engagement and would like to invite you to our next webinar featuring Ben Sigrin of NREL on planning for future DER. This will be held on Wednesday, June 23rd at 4 p.m. Eastern. The next ESIG G-PST webinar will be held on July 14th, featuring 50 Hertz in Germany on STATCOM strategy and application. I'd also mention that we're in the middle of our workshop on meteorology and markets for grid services being held on Tuesdays and Thursdays during the month of June, and all are welcome. Further information on all of our webinars and workshops can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Julia and Jason, I want to thank you again for this very timely webinar and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thank you.